Hi, my name is Kaylee Burt, and this is my Lab Report 6, Magnetic Braking with Faraday. Purpose and preview result. The purpose of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, and then create a similar computational model in ClosScript, and then compare the computational predictions with the observed data from the experiment. The preview of the result, my observed average fall time was 1.304 seconds, and my computational average fall time was 1.435 seconds. The physics principle for this lab, we use Newton's second law to update the magnet's velocity and position in the code. Also, Newton's third law explains how force from the loop on the bar magnet is equal and opposite to the force from the bar magnet on the loop. And then the Bauer-Savart law to calculate the magnetic field of a dipole/bar magnet, the magnetic flux formula, and then the Faraday's law and Lenz's law. Experiment and procedure. The system was a roll of aluminum foil on the bar magnet, the surroundings was everything else, and then here are the initial conditions, and then the procedure was to hold the tube vertically, put the magnet above the top opening, and then record a video of the magnet being dropped through the tube, and then calculate the time it takes for the magnet to fall through the length of the tube. And then we repeated this 5 times and calculated the average time. So this is the observed data. These are the times for each of our trials, and then I went ahead and averaged them, and that's where I got the value that I mentioned earlier. And then here's the ClosScript code I created or edited to kind of simulate the experiment computationally. And then these are the initial conditions and magnetic field and flux. So the initial conditions are here, and then this is the function for the magnetic field, and then the function for the magnetic flux. And then this is the magnetic force calculation. I went in and edited this line to calculate the current in the ring, and then edited the 4 lines down here to compute the B field at each ring. And then this is the rest of the code. I edited these 3 lines to calculate the gravitational force, the net force, and then, like I said, we used Newton's second law to update the velocity and position. Here are the results from my computational model. The measured results, like I said, from the experiment were 1.304 seconds, and then the computational model I got 1.435 seconds. And then this is the velocity versus time graph. You can see, like, at the beginning, there's negative slope. That's because the force on gravity was stronger than the magnetic force. And then the 0 slope means that the magnet has constant velocity because force is summed to 0. And then here's the image, also the results from the computational model, and this is what it looks like as it's running. And then the red current represents the clockwise current from the bar magnet that's creating a magnetic field downwards, and the blue current represents the induced current from Lenz's law in the opposite direction of the red current to oppose the change in magnetic flux. Then potential source of error, the accuracy of the tube of aluminum foil and magnet measures, so the measures we had in the experiment could have been inaccurate. There could have been human error in calculation of the times from the videos, human error in the dipole moment calculation, and then we also could have ran more trials for more accurate results. And then the observed first computational, the similarities, the first 2 times found in the experiment were very similar to the average value time. You can see, like, over time they started going faster. Not sure why that was. Also, both models use the same measurements that we obtained from our experiment, so the same values were being used, and then the experiment end system was the same in both models. And then difference, the average time calculated from the experiment and the value resulting from the computational model were different. Like I said, these are the values, and then the experiment results could be less accurate due to human error, and the computational model could have been more accurate if we had more concrete measurements of the foil's dimensions and the dipole moment. And then what if the resistivity of the conductor were reduced as close as possible to 0? The induced current and magnetic force would increase since there would be more force counteracting gravity because the magnetic force would increase, then the magnet would fall slower. And then if there are holes or slots were cut into the tube, there would be less aluminum to create the induced current, so then the induced current and magnetic force would decrease. Then as a result, there would be less force counteracting gravity, so the gravitational force would be stronger and the magnet will fall faster.